Hello mathematicians. Before we kick off on the Extension 2 maths with regard to mechanics, I think it's worth getting all of our mechanics work together and following the flow. And especially probably this is important for those who don't do physics. So in advanced maths, the focus is on kinematics, which is simply the description of how things move. And to describe the motion, we use terms like displacement. The little arrow up the top here, as we know from complex numbers, means that we're talking about a vector quantity. So displacement is where an object is relative to some reference point. And the magnitude of the displacement is simply distance. Velocity, again a vector quantity, is how displacement varies with time. And again, velocity is a vector quantity, the magnitude of which is referred to as speed. And finally, acceleration, how velocity varies with time. And again, it's a vector quantity. The units are often very illuminating. So for displacement, we know that in terms of SI units, that's measured in meters. Velocity is meters per second, or ms to the minus 1. And acceleration, because it's change in velocity, is ms to the minus 1 per second, which is ms to the minus 2. Now in advanced maths, we only deal with one-dimensional or rectilinear motion. And in this case, our quantities are simply referred to as displacement, velocity, and acceleration. We recognize that we're dealing with vector quantities, but we take account of the vector by indicating a sign, plus or minus, and then it's dealt with numerically, I guess. So displacement is x. We don't have to put the vector notation up the top. Velocity is x dot, and x dot is the notation for the differential of displacement with respect to time. And likewise, acceleration, which is change in velocity over time, is x double dot, or dx dt squared, or I guess we could also have it occasionally, they don't do it very often, as v dot, so dv dt. We have to make sure that we recognise the distinction between dv dt, or x dot, which is the instantaneous velocity, and average velocity over an interval, which is given by change in x over change in time. So if we were looking at a graph of displacement versus time, for example, this would be the slope of the secant joining 2 points, and this would be the slope of the tangent at an instant on the curve. Now there's a similar distinction between instantaneous acceleration, x double dot, and average acceleration, change in velocity over change in time. And once again, this would refer to the slope of the secant on a velocity time curve, whereas this would be the slope at an instant on the velocity time curve. Now finally, if we consider the case of uniform acceleration, then what we're looking at is x double dot equaling some constant value. So a constant value which we'll refer to as a. So therefore velocity, x dot, is the integral of a dt, so it becomes at plus c. And if I adopt the physics convention here, so if the velocity is u when t equals 0, so u is often used as the initial velocity, then at some later time t, x dot equals v, and this equation here becomes the v equals u plus at, which the physicists should be very familiar with. But notice that this equation only applies when we have constant acceleration. So if we change the acceleration, we need to reapply this equation. Now in a similar vein, displacement is the integral of velocity, so it's the integral of u plus at, which becomes ut plus a half at squared. And again, likewise, if we start from the origin, so displacement of 0 at time 0, then it becomes the familiar physics equation, s equals ut plus a half at squared. Now, we can look at some equations here So if we look at a graph of acceleration versus time, that should be v with 1 dot or x with 2 dots. So if we look at an equation for acceleration versus time, and the acceleration is a constant, we'd be looking for a straight line. So if I investigate in particular the case of objects in free fall, I'm talking about uniform acceleration vertically and vertically downwards. So if I adopt the convention that upwards is positive, then my graph of acceleration versus time would look like this. My graph of velocity versus time, so these are all just the wrong letter unfortunately, so this should be x dot. My graph of velocity versus time would look like this. Assuming I fell from rest, then that would be an initial velocity of 0. The slope of my line is the constant acceleration, which is minus a, or even more particularly, it's minus g. And again, my graph of what should be x versus t, or maybe even y versus t, depending on how strict we are about our directions, it's meant to be a parabola, a part of a parabola. So let's have a look at an advanced maths question. Two particles moving along the x-axis, so this is telling us that it's rectilinear, or one-dimensional motion. We've got some initial conditions. When t equals 0, the particle is at the origin, moving with a velocity of +3, so most times we'd assume that means to the right. For t greater than 0, the particle has an acceleration given by this equation here. So part 1, show that the velocity of the particle is given by this. So for this we simply need to know that velocity is the integral of acceleration. So I would encourage you to always put your information down in a diagram. It makes sure that you find every piece of information in the question, and it gives you a sense of the physical setup. So then velocity is the integral of acceleration. We know how to do that integral. We find our constant of integration from our initial conditions, and then we have our equation for velocity as required. Now we're told about a second particle, which is also at the origin at t equals 0, and its velocity is given by this equation. And in part 2, we want to know when the two particles have the same velocity. So obviously that means, when does v1 equal v2? So we simply equate the two expressions, and when we equate the two expressions, the exponential terms fall out. We go down and solve the quadratic, and we see that both particles actually have the same velocity after 1 second. Now finally, we're asked to show that the two particles don't meet for t greater than 0, so don't meet at all essentially. So the trickiest part of this is, what does it actually mean if the particles do or don't meet? When we stop and think about it, particles would meet if they had the same displacement at the same time. So that means that we're going to need to get an equation for the displacement of each particle. So we know that that means that we need to integrate the velocity. So we do that. We use our initial conditions that at t equals 0, the particle's at 0 to get our constant of integration. So we get an expression for displacement of particle 1. Similarly, for particle 2, we get an expression for displacement. And then if they're going to be at the same position, we need to have those two expressions for displacement equal. So we set them equal to each other, do the algebra, and we notice what we get is that for this equation here, t equals 0 is the only solution, because the quadratic part has a discriminant less than 0, so no solution. So these two particles are together at time 0 when they're both at the origin, and then never meet again after that.